Let's solve this geometry problem carefully and pay close attention to the relationship between the three regions, because the main trick is to notice that two of them share exactly the same unknown dimension. We have one large square and it is divided into three parts. On the left, there is a tall rectangle with an area of 12 square units. In the upper right, there is a smaller square whose area we want to find. And underneath that smaller square, there is another rectangle with an area of 9 square units. So the question is very simple. What is the area of that small square? Let's introduce two variables so that we can describe the entire figure algebraically. Let the side length of the large square be p, and let the side length of the smaller square be q. Because the large figure is a square, both its total width and its total height are p. Now, look carefully at the way the smaller square fits into the upper right corner. Its width is q, so the portion of the large square that remains on the left must have width p minus q. The height of that left rectangle is the entire height of the large square, which is p. We are told that the area of this left rectangle is 12 square units. Remember, the area of a rectangle is found by multiplying its length by its width. Therefore, we can write p multiplied by the quantity p minus q equals 12. That is our first equation. Now let's move to the rectangle at the bottom right. This is where the second piece of information comes in. The width of this lower rectangle lines up exactly with the small square above it, so its width is q. Its height is the part of the large square that remains below the small square, which is again p minus q. Notice something important here. This rectangle has the exact same height, p minus q, that appeared in our first equation. We are told that the area of this lower rectangle is 9 square units. So, using the same rectangle area formula, we get q multiplied by the quantity p minus q equals 9. Let's pause here and look at what we have. From the left rectangle, we have p multiplied by the quantity p minus q equals 12. From the lower right rectangle, we have q multiplied by the quantity p minus q equals 9. Now, we could try to solve these equations separately, but that would create unnecessary work. There is a much cleaner idea. Since both equations contain the common factor p minus q, we can divide the first equation by the second equation. This is allowed because the common factor is non-zero in this geometric figure. So, we take p multiplied by the quantity p minus q and divide it by q multiplied by the quantity p minus q, and on the other side, we divide 12 by 9. Now notice what happens. The quantity p minus q appears in both the numerator and denominator, so it cancels. We are left with p divided by q equals 12 divided by 9. And 12 divided by 9 simplifies because both numbers have a common factor of 3. 12 divided by 3 is 4, and 9 divided by 3 is 3. Therefore, p divided by q equals 4 divided by 3. In other words, p is equal to 4, q divided by 3. This relationship between p and q is exactly what we need. We still do not know the individual values of p and q, but we do not actually need to find both of them. We only need the area of the small square, and that area will be q squared. So now we are going to substitute our expression for p into the second equation. From earlier, our second equation was q multiplied by the quantity p minus q equals 9. We know that p equals 4q divided by 3, so replace p with 4q divided by 3. That gives us q multiplied by the quantity 4 q divided by 3 minus q equals 9. Now let's simplify what is inside the parentheses. We have 4q divided by 3 minus q. To subtract these terms, we need the same denominator. We can think of q as 3q divided by 3. So we have 4q divided by 3 minus 3, q divided by 3. The numerators become 4q minus 3q, which leaves us with q. Therefore, the entire expression inside the parentheses simplifies to q divided by 3. So our equation becomes q multiplied by q divided by 3 equals 9. When we multiply q by q, we get q squared. So we have q squared divided by 3 equals 9. Now, we want q squared by itself, because remember, q squared represents the area of the small square. To remove the division by 3, we multiply both sides of the equation by 3. On the left, 3 multiplied by q squared divided by 3 leaves us with q squared, because the 3 cancels with the denominator 3. On the right, 9 multiplied by 3 gives us 27. Therefore, q squared equals 27. And now we have reached the key point of the entire problem. The question did not ask us to find the side length q. It asked us to find the area of the small square. For any square, the area is found by multiplying its side length by itself, which means the area is the side length squared. Since the side length of our small square is q, its area is q squared, we have just calculated that q squared equals 27. Therefore, the area of the small square is 27 square units. That is the exact answer. Notice how we never had to calculate p by itself, and we never had to calculate q by taking a square root. The reason is that the quantity we actually wanted was q squared,